Okay, thank you. So I wrote the kind of summary of the first lecture here. We are trying to understand how bands come from localized orbitals in lattices. And we didn't give a justification, but we said we will give a justification that the most important things, the most important places in lattices are called maximal Wyckoff positions, and they are the positions in the lattice that are left invariant by subgroups of the space group that do not have any other group in between. So in other words, they're maximal subgroups of the space group. So another way of seeing this is to take the subgroup, look at the elements not in the subgroup, but part of the space group. Of course, the identity element has to be in the subgroup, and here is denoted by E. E is the identity. It's, of course, mirror squares to the identity for spinless systems. So the way to see that this is a maximal subgroup is to realize that I can build the full space group by taking two coset representatives. What do I mean by this? There's two elements, identity, which when multiplied by the subgroups gives you just the subgroup, and C2, which doesn't belong to the site symmetry group or the stabilizer group of this Wyckoff position. And when you multiply it by this, it forms the whole group. So since it forms the whole group. Since I only had two elements, okay, there's no way there can be two elements which, when multiplying the subgroup, give you the full group. There's no way I can build a subgroup of this group that contains the site symmetry group, because if I built it, it would have to contain C2. But once I add C2, it's the whole group. So this proves that there is no other group H such that GQ2B, which is C3V, is included in H, is included in G. Okay, so this is a maximal Wyckoff position. I didn't explain why they're important, but they hold a special point in a special place in the group theory of lattices. And from now on, we're going to just focus on this Q2B Wyckoff position. Why? Because the graphene, or like I'm going to give you, we're going to do graphene. The atoms of graphene sit here. Okay? So this tells you everything you need to know up until you bring in the atoms, or like the orbitals. So now I'm going to ask what happens when I add orbitals on these sites. And you can do this classification for any type of orbitals on the site, S, P, D, F, whatever. But I'm going to put in p orbitals, also because graphene is p orbitals. And I'm mostly going to focus, the notes have px and py, but I'm going to focus on pz because it's obviously the most simple, and you'll understand that this is generic. So I'm just going to put pz orbitals. This is the phase of the wave function of the pz orbital. I'm just going to put them on these Wyckoff positions. So say put it here if you want. There's two Wyckoff positions, two sites in this Wyckoff position, 2b. It's got a multiplicity 2, which is given by this index 2. Okay? And now I'm going to ask, what do these p orbitals do when put in this environment on the lattice? So you put it here, you put it everywhere. Well, the zeroth order thing that I need to do is find out how these, so I want to understand what the electronic bands that come from adding pz orbitals on the lattice do. I don't want to write a Hamiltonian. And I claim that I can understand this just from group theory. And the zeroth order that I need to do is understand at least what does one p orbital in the environment of a C3V symmetric site symmetry group do. Because when I put in p orbitals, this feels the structure of the lattice, the fact that I've got other orbitals around, and it reduces the symmetry from SO3 down to C3V which is the site symmetry group of the Wick opposition 2B, or isomorphic to the site symmetry group. Everything that's isomorphic will be this, I'll use interchangeable language for isomorphic groups. Okay, so I claim that it's very easy to understand what happens with PZ orbitals here for both spinless and spinful. And this is a technique known as representation subduction. We'll use representation induction very soon, but representation subduction tells you that basically you can look at a subgroup of a high symmetry group. If you know the symmetries of the high symmetry group, which in this case we know the symmetries of the SO3 has px, py, pz orbitals. All we need to do is just consider the elements of the lower subgroup and particularize the representations of this group to the elements of this group. And then we have a representation for this guy. So it's very easy to obtain representations of this guy. Let's find one of them. Representation number 1, spinless. We're going to focus on spinful electrons, but let's do spinless electrons. Spinless PZ electrons. No spin. My group C3V has what components? Identity. So identity, so call this its wave functions PZ. So identity on PZ orbitals obviously doesn't change PZ orbitals. What does C3Z do to PZ orbitals? What does it do if I rotate a PZ orbital like this? Nothing. So C3 on PZ is still PZ. What does mirror do on this PZ orbitals? This mirror. So I have this orbital and I have a mirror plane that runs through it. Nothing. Okay, so this is one representation for spinless. And of course, we will write these representations as through their characters, and this is very important. The characters are just, representations are just matrices. I'm not going to go through the theory of representation, but representations are just matrices, and they're uniquely defined by their characters, which are the trace of the matrix. So this, we're going to write the representation for C3V. And by the way, this C3V is a group. So here is the site symmetry group, but then when we're going to particularize to the Briand zone, it's going to be the group that leaves some k points invariance in the Briand zone. That group is also C3V. Groups have their representations. So once I write down all the representations of C3V, I'm going to have them both in real space and in momentum space. They're the same representations. Okay? This representation is PZ orbitals, spinless. And I think it's called rho 1, 2b in crystallography jargon. And it's got the characters under E, C3Z, this is the z-axis rotation, M11 bar. And what are the characters? Please. Okay, very good. Let's find out another spinless representation. Another spinless representation is the formed by px and py orbitals. This is the only time I'm going to talk about px and py orbitals. But if you want to, basically, I want to do this representation because this representation will tell you in the end, once I induce up to the band and subduce back to the points in the Briand zone, this will tell you that you have Dirac nodes on graphene. This is exactly the same thing. We're not going to go through it in such detail because I want to go to spinful systems. But px, py spinless, okay? I can choose this basis and look at what my symmetries do on this basis. Spinless. Identity does nothing, okay? So this representation is called rho. It's not rho 1 to b. I wrote it as rho 1 to b. It's some rho, okay? Some other rho. Call it rho 3, whatever. 2b. Identity leaves them invariant, so let's forget about them. Mirror. What does mirror 1 bar do to px? Come on. This mirror. Px is on this axis. What does it do to this guy? Nothing. So this is px. What does mirror 1 bar does to py? minus Py. So in this basis, mirror 1, 1 bar has the representation 1, minus 1. Now this doesn't mean anything. It's a matrix, but it doesn't mean anything because, you know, matrices, because I haven't, you know, if I just had this group, for example, M11, this group is abelian, and abelian things always commute. So the representation is always one-dimensional of abelian things. The only things that don't commute are matrices. So as long as I have just a matrix which is diagonal, this will commute with itself. So this is just, if I just had M11 bar, this would be a two-dimensional reducible representation, not irreducible. But I also have C3, which C3 on the basis of Px, Py does a rotation, and this rotation is cosine of 2 pi over 3, sine 2 pi over 3, minus sine 2 pi over 3, cosine of 2 pi over 3 times Px, Py. Right? Do you believe me? This is just a vector. This is just the matrix of rotation of a vector. That's why. Is the subduction, if I was to give you the rotations of SO3 labeled by an angle theta, you'd put the angle equal to 2 pi over 3, and you'd get this matrix. That's why it's a subduction. You can get it from the... Yes? Does that make sense? Okay. What's the character of this guy? So now fundamental thing number 1. You can see that C3 is represented by a matrix which doesn't commute with this one. So now representation is two-dimensional irreducible of Px, Py orbitals. So I have to be represented by matrices. What's the character of the identity? What's the trace of the matrix of the identity? 2. What's the trace of C3? Which is what? Minus 1, 2 cosine of 2 pi over 3. And M11, 0. So these are two spinless representations of C3Z. Now what we're going to do is go to spinful, which is really what we're interested about. You see, the fact that you have this two-dimensional representation basically will tell you that you have Dirac nodes. Even though here in real space, I only have PZ orbitals. I don't have PX, PY orbitals. The point is, once I induce these PZ orbitals to the full band structure, to the full space symmetry group, and then reduce, that's going to be called a band, or a band representation, and reduce that representation at the C3 invariant point in the Brion zone, not on the lattice, that representation will be this one. So PZ orbitals in graphene in real space transform as Px, Py orbitals, as a representation of Px, Py orbitals at the K point in the Brion zone of the lattice. But this is just mechanics that you can do. But the point is the fact that C3V spinless has a two-dimensional representation is tantamount to the fact that graphene has Dirac nodes without spin-orbit coupling. So spinless. The things that we will use are spinful representations. So let's classify them of this guy. And these are a bit trickier, but we're just going to go through them very fast because I don't have time. The point is, you can do the same story, just not from SO3, but from SU2. So the way you get spinful representations is you define the spin matrices, which are 1/2 sigma x, sigma y, sigma z. These are Pauli matrices. Okay? And I'm going to want the representation of PZ orbitals. So I'm adding on the graphene lattice PZ orbitals, but now spinful. These were spinless. I'm adding PZ orbitals that are spinful. And all I need to do is I know the representations of this guy, SU2. Their rotations by some angle omega around an axis n. Okay? And they look like this. They're e to the I n dot s times omega. This is a number, this is a vector. These are the representations of spin 1/2. Right? It's just, if you put here, if instead of spin 1/2 I had spin 1, I'd obtain the rotation group, etc. Is this clear? Okay? So now we can mechanically get the representation. C3z for pz orbitals. I have a rotation which is around the z-axis, so n is nz. So for this n is nz, and omega is 2 pi over 3. Okay? So this is e to the I 2 pi over 3 times s times sigma z times this 1/2. Okay? That's the C3z representation. It's e to the I pi over 3, e to the minus I pi over 3. It just tells you that spin 1/2 doesn't have 2 pi. The fact that I'm not getting 2 pi, even though the rotation is 2 pi over 3, I'm getting only pi over 3 here, is the fact that I have a spin 1/2. Okay? And it's telling you the spin 1/2 as z rotates by pi over 3, spin minus 1/2 rotates by minus pi over 3. That's a very simple thing. What is it cube to? What is the cube of this matrix? -1, which we didn't have before in the group, right? We had just identity. So the fundamental thing now is we have to add, this is similar to what Professor Atland was saying, C3 cubed is -1, which we'll denote as an element by E bar. Bar means spinful. So E bar is -1. This is -1 as a representation. But as an element is 1, is E bar. As a representation is minus identity, however many. So here is -1, -1. Is this C3Z, if my subgroup, if my site symmetry group was C3Z, would this be would this be a 2-dimensional representation or a 1-dimensional representation, or two 1-dimensional ones? Would this be a if I just had this in my group, no mirror, would this be a 2-dimensional representation? A 2-dimensional irreducible? No? Very good. Why? Huh? It's diagonal, it commutes with itself, it commutes with everything. So it would be 2 1-dimensional representations. But the point is, I have this orbital with its spins fills the influence of the whole site symmetry group, or just think of the site symmetry group as local potentials that are created by other atoms. So I have another element in the site symmetry group, M11 bar, and I need to know what this guy does to the group. And you can justify this in many ways. M11 bar is a mirror plane that goes through this like this, and mirror planes, the spins are spin up and spin down. It looks like they're parallel to the mirror planes, but spin is an axial vector. So what it does is it actually flips under planes that are parallel. So spin up flips into spin down, and spin down flips into spin up under mirror. So it's off diagonal. But you can also do it by the following thing. This is C2 in the 1, 1 bar direction, not the C2 that we have there. C2 is C2Z. Times inversion, it's a composite. This C2 is e to the I 1, 1 bar is x, or sy, 1, 1 bar is y. Sy is, so it's I by this. Inversion doesn't act on spin. By this guy, so inversion doesn't act on any spin quantum numbers. So as a representation, it's just a representation of C2, but a representation of C2 is just rotation by pi, and this I have a pi over 2 here. So this is just e to the I pi over 2 sigma y, if I haven't messed up anything, which I didn't. Right. So this is just I sigma y. Yes? E bar is considered so E bar is a full 2 pi rotation of the spin, which, since the spin 1/2 is not the identity, is minus the identity. So as a representation, it will always be minus the identity as a matrix. But as an element of your group, So there's elements of the group, and there's representations, which are just matrices. But as an element of the group, I have to add an extra element, which is physically means a 2 pi rotation of spin 1/2, and that's called E bar. As a representation, always looks as -1. There is another element, which is the identity. So there's E and E bar. Very good, thank you. There's E and E bar. Okay, so these are the representations of, you can write this down in a representation to be sigma y, sigma x also. It doesn't matter. But now you can clearly see that they don't commute. Okay, is this clear what I did here? I just re-expressed the mirror as a C2 times an inversion. That's always allowed. You can check it based on those, based on these guys. Okay, you can add a third dimension and check it based on inversion is not the same as C2. Okay, C2z. Its inversion flips all the 3D coordinates, and then I express this as a matrix in the same form from the SU2 symmetry group. C2 is e to the I n. This axis is y, so it's n times s. N is just ny times sy, rotation by pi. So I get pi, but I get a half from here, and that's the matrix. Okay, so this is the PZ orbital representations of C3V double group. So I'm going to put this double group means it's spinful. So we call this representation, we call this representation row 6 to be, just for jargon. Yes?
Why doesn't the inversion act on the spin?
So inversion is the purely spatial symmetry that takes all the coordinates to minus themselves. What acts on spin are rotations. Okay, so C2 rotations act on spin. But inversion by itself doesn't act on spin because you can't represent it as just, you can't represent inversion as just rotations. You have to, rotations have different determinant than inversion. So inversion just acts on the orbital degrees of freedom, and rotations and then mirrors act on spin. Yes?
Sorry, in SO3 all the transformations have 1 and mirror, does it flip just 1?
In SO3, so here we're talking, here we have spin, so it's SU2 really. So yes, so say the question, ask the question again, sorry. The mirror symmetry is certainly an element of SO3. It's an element of, a mirror symmetry is an element of SO3. So you're going to have, whatever representation of SO3 was or of SU2, you're going to ask, what does that become when I just particularize to this element? Certainly an element of SO3 or SU2. So that's why I'm actually, if it wasn't an element of this group, I couldn't do this, because here I'm just looking, these are really the representations of SU2, and I'm just, instead of looking at these full representations, I just ask how do they, this is subduction, this is exactly what subduction means. I just ask, what are these matrices when I particularize to these specific groups which are part of C3V? Right, these specific elements which are parts of C3V. C3V is a subgroup of the rotations. Okay, so what are the characters here? Well, I want to, if I don't get to the punchline, this will be useless because it's just a bunch of math. But I don't want to get to the punchline without, it depends how you get to the punchline. It always matters what track you take in life. What are the characters here? 2, 1, and -2. Always this will have the opposite character of this. This is one representation. And we will need for later the other representation. We will need the other representation when, so this is a representation of the real orbital PZ on this with spin 1/2 on this side. This is what I get as a site representation if I put orbitals. So now I told you both the site symmetry group and the representation under the site symmetry groups when I add orbitals. But when I go to the momentum space, I'm going to need another representation, which I might as well of the C3V group, which I might as well just get now, since I'm looking, since I'm doing it. And this is, there's actually two different representations. Can I erase this? Have you guys written it down? Because we're going to like use these. Okay. So there are one-dimensional spinful representations of C3V, and they involve spin 3/2. Okay? So spin 1/2 and spin 5/2 have the same representation, two-dimensional. Spin 3/2 and spin 7/2 have the same representation. So spin 3/2, for example, if I look at the spin 3/2 representation, I can't write it down in terms of 2x2 Pauli matrices because spin 3/2 is a 3x3. So you can write down as 3x3, but I'll just do something. Something simple. I'll just look in the SZ basis. So spin 3/2 SZ basis. I have 3/2 and minus 3/2. Okay, and I now form these states. State plus is plus 3/2 plus I times minus 3/2. And state minus is SZ equals 3/2 minus I times minus 3/2. Okay? I claim that these states are mirror eigenvalues. So M11 bar, so, you know, M11 bar on 3/2 on plus 3/2 is equal to minus 3/2. It flips it. And M11 bar on minus 3/2 is equal to 3/2, but you get a minus sign here, and this minus sign is just because if you apply mirror twice, you have to get identity with a minus sign, right? Mirror twice is identity with a minus sign. It flips the spin by 2 pi, okay? So if I choose the basis where mirror takes 3/2 into minus 3/2, then when I do it again, I have to get 3/2 but with a minus sign. And this is the minus sign here. Because of this, these are mirror eigenvalues. So M11 on plus and minus gives you, and I hope you can, you know, if I did it wrong, you can just correct it, but it's probably, probably true. This gives you I sigma y times plus minus. Sorry, this gives you plus minus. Sorry, this gives you 1 minus 1 times plus, it gives you, sorry, shit. It gives you I minus I on plus minus. Okay? This is what it gives you. These are eigenvalues. So you see, what I've done here is I built eigenvalues under mirror first, rather than here building eigenvalues under C3, just to mix things up, just different bases. Okay? So you would say, well, 2 by 2 matrix. Yes? 1 bar, sorry. Very good, thank you. So you'd say, well, 2 by 2 matrix. So is it two-dimensional? Well, I have to check what C3 does, C3Z. Because, you know, I could have picked the PZ basis here. I could have picked the mirror diagonal by taking combination of 1/2 plus I times minus 1/2. But C3 would have mixed those. So in this case, for spin 1/2, it would be in two-dimensional representation. Here, what you find out is that C3 on plus will give you e to the I 3 pi, e to the I 2 pi over 3, which is the rotation, times 1/2, which is spin, times 3/2, which is the value, this one, times 3/2, which is the spin, times 1/2 times 3. Okay, and C3Z times minus is equal to e to the I minus 2 pi over 3 times times minus 3/2. So this minus. And this is minus 1. This is minus 1. Okay? So you can see that these states are diagonal under both mirror and C3. And this is very easy to understand. These are spin 3/2 states. Okay? The difference between spin 3/2 up and spin minus 3/2 is what angular momentum? 3/2 minus minus 3 half, 3. A C3 rotation cannot distinguish angular momentum 3. In this case, with spin 1 half, the difference between spin up and spin 1 half and spin minus 1 half is angular momentum 1. A C3 rotation can distinguish angular momentum 1 because it transforms non-trivially under C3. So basically, C3 rotations cannot distinguish differences in angular momentum, which are 3 times n. And that's why it can't distinguish this. Does that make sense? Do we need to go through this? Do the words come out and does the writing come out and the words? You are certainly correct. Okay? So is this clear? What I've done is I can pick a basis, look at the action, find of the matrix elements, of the group elements on the basis, and find the matrices. If the matrices don't commute, I have a 2-dimensional representation. For spin 1 half, I 2 them. But I can see that I can build 2 1-dimensional representations, which are really come from the spin 3 half of SU2 through subduction, and these are them. Does that make sense? And tell me if it like there's an answer, yes, no, to this question. Right? Okay, thank you. Yes. That's right. Oh, no. Those are other orbitals. They can come up. I'm not writing all the representations. I'm writing just the ones that I will need. Yeah, so these are tabulated, and you can find them, but I'm writing just the ones I'll need. And these are all the ones that I'll need. Okay, so I have 2 other representations, which are actually called rho 4 2b and rho 5 2b, and they have these characters. They differ in mirror eigenvalue, and the E bar character is -1, -1. So they differ in mirror eigenvalue, and these are our basis states. I've just built them, the full representation. Okay, so now comes the hard part. So these are the spinful representations of C3. Write them down one above, one below the other. We're going to need them a lot. Okay? And I've showed you how to get them by representation subduction, which you'll do a lot more in the future. But now what I want to do is the opposite of subduction. I want to do representation induction, which basically tells you that I now know all the representations here, and hence I know all the possible orbitals that I can have here. Well, all the possible, how the PZ orbitals transform. So I have PZ orbitals, but these are SU2 PZ is kind of an SU2 or SO3 language. So really what I should identify them is by these, rho 6 2b representations. And PZ orbitals are these rho 6 2b representation at this site. But now I know my lattice is a linear superposition of these orbitals on every site. So I have the representation rho 6, this 2-dimensional representation. It was 2, what was it? 2, what was it here? It was 0, -2, what was it here? 1. Okay. 2, 1. Okay, so I have rho 6, 2b. Okay, this is on this side. And what I want to do now is this is called induction, induce this representation in the full space group. What will this give me? What will this give me? This will give me the band, the electron band formed by these PZ orbitals. So this is an electron band. So don't think of bands as diagonalizing a Hamiltonian. Electron band formed by PZ spin 1/2 orbitals at position, sitting at position you know, Q2B in the graphene lattice in wallpaper group 17. Okay? This is it. So let's find out how to do a representation induction. That's a technique that's known for a very, very long time. Representation induction is, so I can write you a formula how to do it, or I can explain physically how to do it, and I'll choose the latter part. But we have to go a little bit fast. What I'm going to choose now is a set of orbitals on the Wyckoff position Q2B, this guy, on which is 1/3, 1/3, which we call Q1 2B. There's another, in the same Wyckoff position, there's another site which is Q2B, call it 2, which is just C2 times this guy, right? It's just this guy. This is row Q2B1, Q2B2. And this guy is just C2 times Q2B, and it's minus 1/3, minus 1/3. Okay? And I claim that just by knowing the orbitals on this side, I can build the whole representation here. Well, that's obvious, because knowing the orbitals on this side, I must have the same orbital on this side. And then I just translate it all across the lattice. This form a unit cell, these two sites in the Wyckoff position, and I just translate the unit cell. Let's do it explicitly. I define with W I1 at position R the orbitals on the Wyckoff position Q1B. I is an index because you saw the representation was twofold. It was a two-dimensional reducible representation. So I, you can think of it as spin up and spin down. It's just the index of the representation. And this is the wave function for spin up on this on site Q. This Q, it probably leaks out a little bit because it's an orbital. You can just take your favorite atomic orbital and put it here and add spin up and spin down. This I for this thing goes from 1 to 2 for PC orbitals, but in general it goes from 1 to the dimension of the irreducible representation, which we'll call NQ. NQ is the dimension of irreducible. I haven't told you why irreducible representations are important, but you can figure out that they're important. It'll turn out they're, all the reducible ones form composite sets of bands. Irreducible, dimension is irreducible of GQ2B. Okay? So if I act with an element in the coset representative of this group, which means an element that's not this G alpha, it's not, well, if it's the identity, it just gives me itself, but if it's not in the site symmetry group of Q1 2B, then all that it does is going to give me another orbital at another position on the lattice that sits in the same Wyckoff position as this one. Right? So for example, the only option there is to act with C2. If I take this orbital and move it to C2, I'll get the orbital here. So that's just saying what I said in words, that a lattice that has orbitals at any Wyckoff position has orbitals at another Wyckoff position. This is just saying that this is an orbital at position alpha. So this is Q2B alpha, where alpha is, in the case of the graphene lattice for Q2B, I just have two Wyckoff positions. But in general, this can go from 1 to the site multiplicity. This is NS is Wyckoff multiplicity. Okay, so if I have a wave function of an atom at the site symmetry group 1 at the Wyckoff position Q1, at the site of the part of the Wyckoff position, site Q1, part of the Wyckoff position 2b, then I'll have another function, another state at this other Wyckoff position here, which is related by C2 symmetry. Okay? Now, since I know the representation, okay, I know that if my element G belonging to C3V, which is the site symmetry group of the Q2B1 position, it's also the site symmetry group of this guy, site symmetry group of the Q2B position. I know that G on the wave function at site 1 at this site, this is just the representation of G. This is just representation theory. Ji W J1 of R. Okay, so what does this say? This is nothing but saying, you know, when I put this, if this was mirror, which belongs to the site symmetry group of this would be off diagonal 1 and minus 1, which is say the spin up goes into spin down, the spin down goes into spin up. Yeah, this is clear? This is just, okay. So now I want to know how the element H, which is part of the site symmetry group of the Wyckoff position 2b, but this other one, the one that lives here, okay, how this acts on its own basis. Okay? So R is positioned in real space on the lattice. This is an element of the Wyckoff position here. This is the element of the site symmetry group of the Wyckoff position here. This site symmetry group is also C3V, but it might have different elements just because this element had a translation. This element might have another translation. It's still isomorphic to C3. I want to know how it acts, what representation, the way it acts here on this, on the Wyckoff position, not 1, but the Wyckoff position 2. So you can make alpha be, you know, alpha is equal to 2 here on this Wyckoff position. But in general, you know, if I chose this Wyckoff position, I would have alpha, or this one, I would have alpha going from 1, 2, and 3. So I is the dimension of the representation, goes from 1 to the dimension of representation. Alpha goes from 1 to the dimension of the Wyckoff position. And this is very easy to find by realizing that I mean, it's some group theory, but we can go through it immediately. And it's in the notes. This is just the representation okay? So if G belonging to the site symmetry group of this site of the Wyckoff position acts as rho of G, then H belonging to the site symmetry group of this Wyckoff position acts what's called as the conjugate representation. Okay? So knowing this group, I can immediately find, knowing this row, I can find this row. Notice that G alpha minus 1 H G alpha, okay? This belongs to belongs to GQ1 of 2b, not to GQ2, right? So I define a representation on GQ1 at 2b of this site. This is rho, and I can find a representation on this site. This is, for example, the simplest example of representation induction, where instead of finding only the representation on this side, I can find it on this side too. Okay? I mean, we can go through it, but it will, you know, it might be a pain. It might be easier to just. I'm not entirely sure. It might be easier to just accept it. Let's just accept it. Does this make sense, though? That knowing the representation that this orbital transforms here, I'll know the representation that this orbital transforms here, because I know the relation between this site and this site. And this is the representation. So H belongs to the site symmetry group of this guy. G alpha, by the way, G alpha is given by, of course, you act G alpha on Q1 2B, and you get to Q2 2B. That's the relationship between them, right? So all you do is, to find an induced representation, you look at the group element that takes one site into the other. You know the representation on this guy. Then you just look at the elements of this group and ask what is the representation of this group, knowing this one and knowing the action that takes me from here to here. And these are the matrices. This is the representation. It's basically just rewriting this representation here in the local frame of coordinates of this guy. This is not the hard part. The hard part follows. Now we know the representations of everything in the unit cell, because the weak oppositions, the multitude of weak oppositions live in one unit cell. So now we have to induce a representation into translations of the full group. So what we don't have is, so we know how the Wannier states, or how the orbital states at site alpha in the weak opposition relate to the ones at site 1 in the weak opposition. But we don't know how the translation relate. But of course, the translation are just another group element. We call them identity times translation mu. That's a group element of the full space group. And the way they relate orbitals is the following. By just translation. Is this clear? The reason for this is if R is in the mu, is in the, I know this is in the first unit cell. Okay? Or some unit cell. I know it in one unit cell. All I need to do is translate the hell out of it, and I get how these Wannier states are in all unit cells. Does that make sense? This just tells you that if R is in the Muse unit cell, right? If this is the element in translating the Muse unit cell, this is the same as the one in the first unit cell, because R minus T mu brings it back to the first unit cell. Okay? Knowing this, I can now build the full representation, the full band representation, and let's just do it. Let's just do it. And what we're going to do is build it in momentum space, because I want the band. So what we're going to do is we're going to use the momentum space functions AI alpha of K and R. This is momentum. This runs from 1 to the dimension of the representation of the site symmetry group, and this runs from 1 to the number of sites in the Wick opposition, to the multiplicity of the Wick opposition. So, what would be this matrix in terms of I alpha for PZ orbitals, in spinful PZ orbitals in graphene? Well, PZ orbitals, spinful PZ orbitals, have 2 spin up and down, so this goes from 1 to 2. But they also have 2 weak, if they sit at PZ, if they sit at 2B, they have 2 weak opposition, this and this one. So this runs from 1 to 2 also. Okay? So the basis state would be a 4-dimensional vector, and I'll show you the representation is 4-dimensional, the band representation. So in other words, I have PZ orbitals here, up, down, PZ orbitals here, up, down, 2-dimensional representation, 2-dimensional representation, 4-dimensional representation total. I'll have 4 bands that connect through the Briand zone that you can say. Okay, so this guy is the following. It's just a Fourier transform over the whole lattice of e to the I k translation vectors. This T mu are integers of the lattice constant, Wi alpha of r minus t mu. So these are atomic orbitals. If I know them at one position, I can use group theory, and I know them at one position because I have the representation of the site symmetry group. I know them at all Wyckoff positions in the unit cell. If I know them at all Wyckoff positions in the unit cell, I just translate them everywhere. I form a band. This is the K momentum Fourier transform of the orbitals in real space. And what I need to do is find the action of an element. What I need to do is find the action of an element of the space group on these bases of states. These are bases of states. I need to find the action of an element of the space group on this basis of states. So I told you that the space group G is just a union of coset representatives, which in this case are 1 and C2, times the site symmetry group. Okay, so what I need to find is the representation. Now I call it a representation of G, because I've induced it into the full space group, of the element H, which belongs to G. G is the full space group, times this base times this, the A, I alpha, K, and R. Okay, this is what I need to find now. I need to find the expression of this matrix, knowing the expression of this matrix. Okay? That's a complicated procedure mathematically. Well, not complicated, very algorithmically simple, but complicated to explain in 10 minutes. It's written down. I'm just going to give you the expression. But basically, it's very clear what we're trying to do. We're trying to get to the representation of this big space group from knowing representations of orbitals of site symmetry groups. And that's called representation induction. And it's got this form after you do some algebra. It's got this form. Rho G of H. It's got two. Its index is given by two sets, right? Because one of them runs through the I and J run from one to the representation to the dimensional representation of the site symmetry group. Alpha and beta go from one to the multiplicity of the Wyckoff position. It has a momentum because it acts on something with a momentum. So this is e to the r k, some translation vector that I can give you, times rho ij, g beta to the minus 1, e minus t beta alpha, h g alpha. Shit. Rho ij, g beta to the minus 1, identity minus t beta alpha, h g alpha. Okay, so this has a lot of indices. What does it mean? Well, R, this R is the rotation matrix of this element. This element is H times some translation of the space group. R is this R. T beta alpha is a vector that relates how this element has moved the Wyckoff position from alpha to beta. So T beta alpha is, oh, come on, I think T beta alpha is this matrix element on the Wyckoff position Q beta minus Q alpha. Okay? And once you know alpha, you can determine beta by the requirement that this group element, this is a group element, this group element has to belong to the site symmetry group of Q1 to B. Why? Well, all we know is this matrix. I know only this matrix. So whatever I put, this is ij, whatever I put as the argument of this matrix better be in the site symmetry group of where I started from, of this guy, okay? It turns out that this is a one-to-one decomposition. Coaster decomposition is, you know, well, it's not unique, but coaster decomposition is actually unique. But so the point is something else not unique. But the point is, once knowing alpha, there's only one beta that satisfies the following condition. So if I know H, which is an element of the space symmetry group, and I know alpha, I'll be able to tell you what beta is. For all other betas, this matrix is 0. So this is how you induce representations. Okay? So now I have this matrix is a huge, well, this matrix is a matrix of n times nq by n times nq, and it's at every k by n sites times n sites matrix. This is a huge matrix. And that matrix is called band representation. Yes? So, sorry, yeah. RK. This is a number. This is a rotation matrix on K, and this is a vector, and this is also a vector, because it's... These are two components vector in 2 dimensions. Sorry, beta alpha. So this is for each beta and alpha, this is a vector. T beta alpha is this. Right? These Q's are vectors. Q's, the Q's are the positions, the site symmetry, the Wyckoff positions, they're vectors. For each beta and alpha, okay, which run between beta and alpha run between 1 and the multiplicity of the Wyckoff position. This is a vector for each of them. This is a number. That's right. So this is the matrix. So let's see what it does here, right? So let's compute T11. T11 for the graphene lattice. Okay? So T11, and I'll compute it for H is equal to C2, right? So H is equal to C2, so H does not belong in the site symmetry group of this guy. So then what it does is it sends, this is C2 times Q1 to B minus Q1 to B. So this is Q1 to B is 1/3, 1/3. C2 times Q1 to B is minus 1/3, minus 1/3. So this is minus 2/3, minus 2/3. So it's the vector minus 2/3 times E1 plus E2. And then you just dot it into K. That's just basically telling you that, you know, this is really nothing but representation induction. It's just that you get these annoying phases because of the translation group. But these annoying phases are important at different points in the momentum space. That's right. That's right. So I mean, these are basically so the reason why you compensate between those is basically also because you'd Fourier transform your Hamiltonian, right? So this is nothing else but a Fourier transform. I'm just not doing it in the Hamiltonian. But that's intuitively it's basically it's exactly this thing. It's basically if I Fourier transform this site and then Fourier transform this site, they're going to get a factor in between them of the difference between these guys. And those factors are important at different points in the Brillouin zone. So that's exactly the point. Okay? Very good. So I'm going to take 2 more minutes because we started 2 minutes late. So, and Titus doesn't mind. Oh, coffee doesn't mind. So, okay. So now, this guy, which is a k-dependent matrix, is called the band representation. So I'm going to tell you what we do from now. So this is a band representation, and you should think of it as a k-dependent matrix that runs around, so rho of H of G, which has an index k and indices j beta, j alpha, I alpha, which is an n dimension of the site symmetry group representation times the Wyckoff position square matrix for every, it can be 0 if, if there's nothing that relays these two, it's 0, etc. So you can just, I'll work out an example later. But the point is, this is a band. This is how you define bands. So now this is a momentum space. So the next thing that we're going to do is go immediately to momentum space and ask, I have this band defined over the full Brillouin zone. What happens when I'm drawing the Brillouin zone of the graphene lattice, which looks like this, is rotated by 90 degrees from that? This is the Brillouin zone of the, okay? What happens to this band representation when I particularize 2 points of high symmetry in the Brillouin zone? Okay? So now what we're going to find is we're going to find how the band decomposes at high symmetry points in the Brillouin zone. Next thing, so I'm going to work it out. I'm going to work out how it decomposes. You're going to see that it looks nothing like the Dirac points of graphene because this is spinful graphene. It's got spin-orbit coupling. And spinful graphene looks nothing like graphene. And you'll see this. Or nothing like graphene you used to. And then we're going to ask, what does this band representation really mean? And the moral of the story is that you can see that it's at each k, this particular band representation is a 4x4 matrix because I have 2 Wyckoff position and the representation of the high symmetry of the stabilizer group was 2-dimensional. So this will mean that graphene at every k has 4 bands, and that these bands, if they come from localized orbitals, which is the way I built this representation, are connected in the Brillouin zone. So the dimension of the band representation tells you the connectivity of the bands in the Brillouin zone. Okay? So as I go, because it doesn't know about, the k is just the number there. So whatever, so basically this is going to be called an elementary band representation. And it's elementary because I've chosen it to be induced from maximal Wyckoff positions and irreducible representations. And that means that all the bands that come in it are connected. We're going to find in the next lecture a second set of bands that don't look like they're connected. They look like this. Okay? That if I look at them together, they're indistinguishable from these 4. But you can see that they're disconnected here. And what we'll be able to prove is that these have to be, by default, topological. So why are these band representations good? Well, they're good because they tell me what comes from maximally localized Vanni orbitals. What comes from maximally localized Vanni orbitals cannot be topological. So anything that doesn't come from a band representation has to be topological. And we'll find out everything that cannot come from. So far we've just basically modded out the trivial parts of the problem. So basically, again, all I've done is I've put orbitals on lattice sites, induced the representation to the full group, identified a band with a representation, and then told you that bands that come from maximal Wyckoff positions from irreducible representations are connected. I didn't prove this to you. I'll prove it. But then there is a second set of bands that cannot be induced from real space, from this local orbitals. And I'll prove that they exist in momentum space, or will prove that they exist in momentum space, that look like this. And since they cannot come from localized Vanni orbitals, because we've showed all the ones that can come from localized orbitals, they have to be topological. And that's the moral of the story that, let's hope we'll get into by the end of the next lecture.